Hey Raiders. In this video, we're going to take a look at analyzing what I'm calling a level 2 cliff scenario problem. That's where, unlike a level 1 problem, which is the simplest, where a ball is just dropped from a cliff where the initial velocity is 0, a level 2 problem is where the ball is thrown vertically, either upward or downwards, with some velocity. Ultimately, a level 3 problem will be where it's launched at an angle, but we'll cover that later on. So let's say we have a scenario where we have an 80-meter cliff, and the ball, instead of being dropped like a level 1 problem, is thrown upward at 15 meters per second. You'll see in a minute how this is ultimately a little more complicated in terms of how we're going to analyze it. So in this kind of scenario here, you could ask a couple different things. One of the things we'll take a look at is how much time it takes for the ball to hit the water. And we could also take a look at how fast is the ball going when it hits the water. All right, so we're going to take a look at this one right here. How much time does it take for the ball to hit the water? So again, we're going to apply our problem-solving technique. We're going to identify what information we're given in terms of our equation variables. So unlike a level 1 pulley problem where the initial velocity was 0 because we just dropped it, here the initial velocity is 15 meters per second. And velocity is a vector quantity, direction matters. Since the ball is launched upwards, it's going to be a positive initial velocity, as opposed to gravity pulling down on it, which will give it an acceleration that's negative because it's accelerating it downward and 9.8 meters per second, or 9.8 meters per second squared. And then displacement is not going to be 80 meters. Displacement is where something ends up compared to where it started. Well, it ends up 80 meters below where it started, so displacement's negative 80 meters, not 80 meters. And then we want to find, in terms of our equation variables, at least starting off, t. How much time it takes for the ball to hit the water. So if we look at this combination of variables that we either know or that we're looking for, and then we kind of match that up with our equations that we know, we'll see that we can use the quadratic. D equals VIT plus 1/2 AT squared. So substitute your values in and see where this takes you. So negative 80 equals 15t plus 1/2 times negative 9.8 t squared. Now when we did the level 1 problem where the ball was just dropped, the initial velocity was 0, this term went away and that simplified this algebraically. It was pretty easy to isolate this variable t. But here, since it shows up in two different places, t and t squared, here's where we're going to be using the quadratic formula. So if you remember, if you put this equation in standard form, and when we talk about standard form, what we really mean is it's got to be in the format of ax squared plus bx plus c equals 0. So for our equation, we're going to simplify this. 1/2 times negative 9.8 is negative 4.9. And since that's the coefficient attached to the squared, that goes here for the a. So it's negative 4.9 t squared plus 15t. Now we have to make the equation equal 0, so adding 80 to both sides will be plus 80 equals 0. So here's your a, here's your b, and here's your c. And these could be what we could use in the kind of tedious quadratic formula of negative b plus or minus radical b squared minus 4ac, that quantity, and then all over 2a. And we could do that, kind of methodically work our way through here and figure out what value or values of time make this equation true, meaning when the ball will hit the water. But to save time, we're going to either solve this using a website like Desmos, where we'll be able to input this equation just like it is and click on the appropriate points in the graph to find the time, or we can use the quadratic formula program in a graphing calculator. So I'll just kind of walk through that. There's a million little variations of this you can find or kind of create. So here under program, Quadtic, that's us. Now that we've already put our quadratic formula equation in the standard format, now we're ready. So we're A equals, that's going to be negative 4.9. B equals, that was the initial velocity, 15. And C equals, the constant there, is 80. So when we hit enter, you're going to get two possible values. And here's one of the examples where you have to kind of separate the pure math from the physics application of it. Negative 2.79 is an appropriate value you can substitute in for t to make this equation true. But since we know in this real life scenario, t represents time, we can't have negative time. So the time the ball's in the air must be about 5.85 seconds. Now, just quickly, if we wanted to figure out how fast the ball is moving when it hits the water, once again, we'll identify what we're given. And that hasn't really changed. The initial velocity, the ball was thrown upward at 15 meters per second, so that's a positive value. Since velocity is a vector quantity, direction matters. It's going to accelerate downward. Gravity will pull it down and speed it up at 9.8 meters per second, or 9.8 meters per second squared in the negative or downward direction. And displacement, again, it's going to end up 80 meters below the height from which it was thrown. So that's negative 80, and we want to find VF. Now, a common misconception here is to think, oh, the ball's going to hit the water and stop, which is true, but these equations are set up to analyze its motion in the air. So when we say ball's final velocity, we really mean the millisecond before it hits the water. So if you apply the problem-solving technique where we identified what variables were given, what we're trying to find, and now match it up with our equations to see which one ties them together, and then we come to this conclusion, VF squared equals VI squared plus 2AD, and we're looking to solve for VF, final velocity. That's our unknown. So VF squared equals 15 squared plus 2 times negative 9.8 times negative 80. So work out some of this arithmetic here. So we're going to have VF squared equals 225 plus 1568. So we have final velocity squared equals 1,793. So now we'll take the square root of both sides. And the final velocity is approximately a quantity of 42.3 meters per second. But just by the nature of this, when you work this out in a calculator, the square root, you're going to get a positive number. But we know the ball's moving downward when it hits the water. So we're going to manually add in the negative sign ourselves to show direction that the ball's moving about 42.3 meters per second on the way down as it hits the water. All right, as always, if you have any questions, you know how to get a hold of me. Take care.